So what we're going to talk about, you've heard a lot about phased array this today probably in here, so we're just going to walk through some of the power plant applications that are currently being done in the industry and walk through some data and some follow-up data from indications and components we're monitoring. So AIS just is a company. We're just a field service company. So we're in the field. We use advanced phased array ultrasonics for a lot of different power plant applications. So at the core, that's what the company is. And so what we're going to talk about is just some case studies on some different components. That's bypass valves, T-crotch cracking, HP steam drums, and some header end caps. Some of you guys in the power industry are probably familiar with some of these. So we're just going to walk through some of the phased array techniques that were used to find some of the flaws. So the Advanced Technology Center, where a lot of these techniques were developed, is in Charlotte, North Carolina. And the goal is to, if a customer comes and has an issue or has a flaw that they don't know how to inspect, we come up with a technique that can inspect them. And a lot of times the fastest, most economical way is usually with a phased array technology. So that's kind of where a lot of these are coming from. So the first one, we're going to talk about bypass valves. So in the power generation, there's this particular case study. We're going to talk about a bypass valve that had a previous failure. And in the process, they come back for follow-up inspections to verify the repair weld was holding. And during the inspections, we discovered that the weld repair was fine, but there was a lot of cracks in the rest of the valve and in the surrounding downstream of the valve. So the question was, well, what can we do? How can we mitigate this? There's a 2-year lead time on a replacement valve. We can't shut down for 2 years and wait. So in this image, you can see the original weld repair. And the intent was we need to know how bad it is. So what we did from a condition assessment standpoint, we go in, we do the phased array inspection. The damage is a lot worse than they anticipated, so the question was why. So we went in with a lot of different techniques. We did mag particle, we did the PMI gun to verify the materials. We also took some replications because it was supposed to be a grade 91 material. When we took the replications, certain acid etchants work with certain materials. We etched it based on grade 91 material, and it wouldn't etch. So that's our first red flag. Maybe you have the wrong material. So they wanted more confirmation. So after that, we went back with the PMI gun, verified the material, and then come to find out they were using 2 different materials. So you can see this here was your grade 22, grade 91. So the weld material in some of these were different. So that's why one was a lot worse than the other, comparing unit 1 to unit 2. So this was the material breakdown, and it's probably kind of hard to see in that, but you had one material, another material on the base or the body of the valve, and then you see the hardness readings were not anywhere close to what a grade 91 hardness should be. So that was a third red flag that, or confirmation at this point, that was the wrong material. So what were the results of the phased array inspection? So once we finished scanning, you can see there was essentially a damaged valve. So there was a quench cracking downstream of the valve from the water getting through. So you can see down here, we laid out a lot of the large cracks. So 50% through wall on a quench crack is pretty significant crack. They couldn't operate with those conditions. So we had to lay out all of the indications so they could come up with a plan to do a repair. In the upper half, you can see here, it actually was a crack coming out of a short counterbore. So if you look here, the thickness transition was huge from one material to the other. So that in itself was a stress riser and made the repair wear pretty difficult. So so this was the data. We were scanning circumferentially and actually around the part. You can see here, looking actually around the part, this is encoded data. You can see multiple cracks running down the surface. This is just standard phased array. There's nothing fancy about it, just encoded data. Scanning from both sides. And then we also scanned actually around the part, looking for cracks running down the length of the pipe. And you can see this was a time-based scan, so it's not a very good encoded scan, but you can see multiple cracks as we went around the circumference looking for these cracks and down the length of the part. So you can see here. Now the question was, what do we do? We get the metallurgist involved, and the only way they could continue operating was to put a weld overlay. You know, anyone from the nuclear industry is probably familiar with weld overlays. What we would do is they put a DMW weld overlay, basically a grade 91 that covered the grade 22 and the grade 91 material. And the engineers came up with the need to be at least about a 1/2 inch in thickness, 5 inches long to cover the affected area and to meet the requirements for the remaining good wall. They also wanted to perform inspections of these as we go. So a critical part for phased array, any phased array, basic or your advanced techniques, is the surface condition. So the welders, as soon as they finished, they said, okay, it's good, it's ready to go. Can you go inspect this real quick so we can get moving? Well, clearly all of those, it's a good weld, but it's clearly not a surface for a phased array technique. So we said, okay, we need you to flat top this. You know, we need a good surface. They did a little bit more. Let's see how much we can get away with. They flat top it a little more, better, but you're still going to have a lot of issues with those little grooves there. So finally, after the third attempt, they gave us a good quality cleaning, which they could have done the first time, but now this is how it goes. Didn't take too much extra time. They got the weld prep cleaned, and then we needed to come up with a scan technique to verify the weld overlay quality plus the initial cracks, making sure they've not got any worse due to the heat and post-weld heat treating. So with this technique, we decided to scan in multiple directions using the TFM, FMC, and standard phased array approaches to cover the weld overlay section and verify the initial weld material. So some of the images of that, you can see looking through the weld. So if you can, I don't know how well you can see it back there, but you can see there's a kind of a line here and then a vertical line here. This line up, that's all weld overlay. This is the fusion line of the original weld. So our setup told us that our sensitivity was high enough. We can see the grain structure changes. We were confident if anything had changed from the weld overlay that we would be able to pick it up. Looking from both directions, you can still see the original cracks were there, and comparing them to the initial data, they had not gotten any bigger, so we were confident that the welding process and the post-weld heat treat had not changed the original cracks. And so this was a 1.5 year later follow-up inspection. So we went back, so this was the original data. Now, these two images, it's the same flaw, but it's a different system. One was that were just taken with two different phased array systems, but the data looks very similar. You can see the cracks have not really changed from a 1.5 year difference. You can see everything's basically in the same place, the same height. So they were confident that a 1.5 years later, they were good to go. I think before they get their replacement valves, we're going to do one more verification check. But so far, the weld overlay worked, it did its job, and it allowed them to continue operating until they could get the new valves in place. And it's just some more from the other unit. We're monitoring 2 units with the same problem. All the indications are still roughly the same. And this is the same issue, but a different plant where they decided to leave the flaws in place, not do a weld overlay and take a chance. This is a third phased array system, but these had some of these were almost 80% through wall. So the downstream quench cracking is a pretty big issue, and they can grow through wall pretty significant. This was not in the United States, so I have not heard any follow-ups on that to this point, but I'm sure we'll hear from them if they do have a failure. The next one, the Form Ts. So the Form T crotch cracking is a relatively new issue. Not really new issue, it's new to the NDT world for us. It's not a typical inspection when you go to a high energy piping exam. We usually don't look in the crotch area. The crotch area is not typical. We usually look at the adjacent welds, MT, do the UT thickness, and we'll do phased array of the welds, but not the crotch area. So even new Form Ts, even new Ts could be prone. I'm not a metallurgist. But the backstory is some of the technology, some of the T forming processes that were with the original manufacturers never made it to code, never transitioned to the new generation of people. So the issue is of the T crotch cracking still exists in some new Ts. So this T here was used by a metallurgist of ours. They did a lot of work to it and they wanted us to see, well, can you do a phased array inspection on this? So yeah, 10-inch diameter T, 1.8 inch thick, grade 91. It was removed from service. So this is how we built the technique. You can see the cracks on the inside in the crotches and both crotches. Unfortunately, from a technique development standpoint, this was not the best sample because they were very large cracks. It's not very difficult to find these, but it gave us an idea of how to develop a technique and accurately find these cracks. So this is the approach that we took scanning wise. Is the issue here was probe footprint or probe size versus thickness. Typically the thicker material, your probe gets a little bigger because you got a bigger aperture, bigger pitch. Well, we didn't have that luxury here. There was not much room in the introduction to some of these Ts, so we had to keep the probe small. And working with the materials lab, working with some EPRI recommendations, we were able to come up with a technique that allowed us to get to the ID of these Ts to find the cracking. So this is the cracks in the sample we were just looking at. Very large, very easy to see, but it was a proof of concept that, yeah, even though it got a complicated geometry, it's not the smoothest surface, we can still get a probe on there and perform these inspections. So just an overview of what we were looking at from a little easier to understand, the cracks going right through the center of the crotch area to the ID. So there were ID to OD propagation. And we would set our probe in the crotch area where we could fit, where it was flat, and we were able to detect the cracking. Now, there was a lot of different ways in the what they did with the Ts. Some left them, some did weld repairs, some did some other things, but based on the way these things crack, the things that we were told from a service company is that you should perform a full condition assessment of the T, which included material thickness of the body of the T, the thickness, a very small grid in the crotch of the T, do some hardness readings, do some PMI readings, MT or PT of the adjacent welds and the crotch area. And that was the difference. You know, we usually would never MT the crotch of a T. That's not a standard approach. But with the EPRI recommendations and some of the materials engineers we work with, that's the inspection approach we took. So if you do all of these together, that will get you in the, get you a good condition assessment. So from the way I understand as a non-metallurgist, the thickness of the body of the T and the crotch of the T needed to be within 30% of the same thickness. If they were not, which a lot of the times they were not, that's created some of the stress risers that led to cracking. So that's why we do all the additional steps with the mapping of the T body and the crotch area. And so this is just some of the data that we have taken. So you can see the grid layout here, the smaller grid and the crotch areas, just to give them a good idea of the configuration of the T. And this is some data of a good crotch area. So this is what you want to see when you're doing the phased array scan. These are the adjacent welds. You can see some welding flaws, some small things in the weld material, but nothing severe. And then this is what you see if there's a crack T. So in the upper image, you've got standard phased array here, standard phased array down here. This is the smallest we've been able to detect in the field. So this one measured to about a 1/2 inch through wall, and the previous ones were like 1.5 inches through wall or so. That's some of these larger cracks here that you can see. You can see it moving. This is the TFM setup in these two images. That's conventional phased array, and there's other images. Now, would we have missed that with conventional phased array? No, probably not, but that'll help for monitoring if I decided not to remove it from service. And just some other images. So this is the smaller flaw we were detecting. It was measured at about a 1/2 inch in one of these T's, and that's kind of the configuration. So it's pretty small. It's not a very uniform configuration. So it's definitely takes the technique and some prep work to do an inspection on those. So to this, that's about the smallest as a level 3 that would be working with our guys. Like, don't tell them you can detect anything that we can't prove. So the smallest we can prove that we can find would be a flaw about 1/2 to 3/4 thickness. So that's all that we've been able to do. I know you can do more, Jay. We work with Jay a lot on these technique development type work. So the next one is the steam drum nozzle cracking. So unfortunately, this unit did some inspections and the head to shell weld on this HP steam drum cracked halfway around. They had to do a major repair. They had to post weld and preheat the entire end of the shell. I mean, this is a large 6-inch thick part. And then unfortunately, a welder had to get inside of this thing and weld it while it was at temperature. So it was not a good scenario for any of them. So the issues that we're seeing in the field is sometimes they don't want to go remove all the internals to create a confined space, to take out the belly pans, to do internal inspections. So the question was, well, can you do the inspection from the outside? Like, so we can try, phased array technology is capable. So that was the reason why. We wanted to be able to offer utilities, customers, options to do the inspections from inside the drum, looking at the outside welds, or from outside the drum, looking to the inside of the welds. Now, obviously it eliminates the surface inspection, but if you have cracks, then it is something you can monitor from one surface. So this is just some images. You can see the cracks from the inside of the drum. And this is a little repair weld here that they put in. You can see some cracks on this nozzle. So one of the first situations we looked at is a company came in and each one of these drums had about 18 nozzles total, and the company rejected 18 nozzles, 360-degree cracks. So FYI, if it's 18 nozzles, the same crack, 360 degrees around every nozzle, it's probably not. They're probably seeing something else. So they wanted another opinion. They brought somebody else in, did the phased array inspection, and they didn't know, or the original company didn't have drawings. So they didn't know if it was a full penetration weld or partial pen. So the first thing was we went in with phased array. We were able to determine it was a partial penetration weld. So you can see here, there's a little corner trap there. So right here would be the bore of the nozzle going up. This is the weld on the OD of the actual drum. So it's with the right phased array setup, it's pretty clear to see that where the weld material is at. Now, this was the nozzle where the weld stopped, basically the root of the OD weld. This is what the previous company was calling a crack, and they called that a crack on all 18 nozzles. So it's not a crack, it's the root area of a partial penetration. The actual crack is right here, which was on the inside of the part. So this is an image looking with a small footprint probe, sweeping our angles up pretty high, just to see an OD connected crack to verify that it was there from the inside of the drum. So overlaying the data, this is what they were seeing here. They were scanning from the inside. They were seeing this nozzle wall here, calling that a crack because they didn't know the configuration of the weld. So it wasn't all the technician's fault. They know what they know, but if they didn't have drawings. This is overlay showing the OD weld, so it maps out pretty good with the drawings that they were able to find. So that just confirmed that you can see the ID roll here. So that was through 5.5 inches of material and still get pretty good resolution down here in the weld area. Now the next one, similar process, but this nozzle was a full penetration weld. So this is the configuration of this weld. The customer also didn't have drawings. They didn't know what type of, the plants get sold, they get moved. They didn't realize what they had. So the first step was to go in and tell them what type of weld they had. So we just went in with our phased array from the inside of the drum, and it's pretty clear to see from a phased array technician, you can see the outline of the weld really nicely. This is the nozzle bore here. This is the weld heat affected zone area, so it's clear to see that that's a full penetration weld. So that was the easy part. Then we had to confirm whether what type of flaws we could find. So just an overlay for the ones that are not real familiar with phased array. We're shooting from the inside. You can see the overlay, and it matched up really well with our phased array data to confirm that it was a full penetration weld. So now, this particular case study, a company had previously gone inside and done magnetic particle on the inside of the drum, verified that there were some small cracks. The plant was willing to clean it up for us and allow us to come scan it from the OD of the drum just to see if we could find the same cracks with phased array. So this is kind of what we were looking at, shooting from the OD, looking through to the ID. You can see there's a lot of, the welds had a good bit of weld imperfections, slag, porosity, stuff like that inside of them. But scanning from the outside, we were able to shoot in and see this is kind of the root area right between the two welds. We can see, so looking, this is the inside, this would be the OD. So we're shooting through the material, and you can see the little corner traps from the welds, same way here and up here. So we were able to go in and confirm that the nozzles that had cracks, we were able to see from the outside using the phased array technology through about 6, this one was pushing 6 inches in material, 6 inches of steel, just your basic grade 22 steel. So with the right setup, with the right transducers, you can shoot through a lot of material and you can find fairly small indications. Now, the last one, I have no idea what time it is, so hopefully I'm doing okay on time. Okay, so this one, the header end cap. So this has been an issue in the HRSG combined cycle plants. We work with EPRI on this. We do some work in the field inspections. So some of these, what's that? Yeah, so apparently no one's fixed it yet. They're still cracking. The cases we've dealt with, some of these have completely come off. We've had situations where we found cracks, told them they need to do a repair, they start machining the weld out, and then the header cap just falls off. So pretty large cracks. Luckily it's contained, it's not really in an environment where people can get hurt, but it causes damage to the plant. This is just showing, this is a thing from EPRI showing the different types of configurations that can be used in these end caps. And it's the one with the little notch here, the plate style, that causes the most issues with a little corner trap right there. So the best thing that we could come up with is we got an end cap from a customer. They sent us the end cap machine just like in their plant. We got the material, just the regular material for the header. We made a mock-up with flaws in it. So we were able to validate the technique that we came up with and test our guys that are going to be going out and doing the inspections. So those that are not real familiar with these, if you look here, these things are very close together. So you can't get 360 degrees around doing a normal inspection from the header side. So the technique that we ended up going with was scanning from the end cap side, looking through to look for the cracks. So that was the reason why it was difficult. Some people inspected these, called them good. Oh, it's limited, but what we scanned was good. A couple months later, they would fail because there was a crack on the bottom. So we needed a way to do a full volumetric examination to really check the quality of these things. So that's what we did with the mock-up. And this is just some data overview. So where we had access, we could scan from the top. And these are actually indications from the field. This is data we've collected in the field. Pretty large cracks, and we can find them from the end caps. Where we have access, we can scan from the header side. And yep, that's it. So any questions on any of this stuff? I know there's a lot of information really quickly, but I'll be around if you guys have any questions afterwards. All right, and that's it. Thank you.